All right, so I can see NB, Jade, Maxon, and Sai now. I do have a couple of technical issues on my end that I'll have to sort out before next week, so I won't be drawing with a pen, but other than that, I think we're all set. Does anyone have any questions from the homework before we get started? Okay, so no questions from the homework. This week was all just derivative and integration rules. So let me go ahead and we'll pull up just a formula sheet and go through that first, I guess. There we go. Okay, so lots of derivative and integration rules. Is there anything terribly new here that we haven't covered before? So let me start just in the middle. What happens if I derive a to the x? Let's go down the line. So NB. Oh. Oh, there we go. Okay. NB, what happens if I derive a to the x?
X minus 1.
So if I derive a variable to a power, then I'll end up with, in this case, nx to the n minus 1. But if I'm dividing a real number to a variable, then something different is going to happen. So this would be something like, we'll say a is 4. If I derive 4 raised to the x power, what would happen?
Four to the x times ln 4.
There we go. So if I derive a to the x, then this should be a to the x ln a. Over to Jade, if I derive log base a of x, what's going to happen?
Uh, 1 over x ln a.
Okay, that's good. If I derive arc sine of x, let's go Maxon. Actually don't remember. So did we do the inverse trig functions in pre-calculus or not?
No, I don't think so.
Okay, then let me start from scratch on these ones. So if I have a function, we'll say y is equal to the arc sine of x for this one in terms of x. So if I want to derive this, the first thing that I'm going to do is I'm going to go take the sine of both sides. So if I do, that's going to give me with the sine of y is equal to x. Okay, from here, Maxon, what can I do? So goal
in
is
the end, goal, yeah, in the end, are we trying to find dy over dx?
Yes.
Okay. Derive both sides.
Okay, so what happens if I derive the sine of y?
Cosine of y.
Okay, I'm gonna get the cosine of y and then chain rule. So cosine of y times,
Dy over dx.
that's it, dy over dx, it's the one we're looking for, and then equals,
Equals to 1.
1. Okay, if I was going to do this implicitly, then this dy over dx would have equaled dx over dx, since we were deriving in terms of x. We don't need to write that though, because we're already in terms of x. Dx over dx will cancel and become 1. So what I'm going to do is I'm going to draw, attempt to draw, there we go. I'm going to draw a right triangle relationship. If I make a new line, then it'll let me draw. Okay, I'm going to draw a right triangle relationship using our second line that we have here. So the sine of some angle y is equal to x over 1. I'm going to jump over to, oh, got someone else coming. I think that's Nani. Either Nani or Nicola, I'm not sure. Hello. Okay, I'm going to jump to sine next. So this is the sine of some angle y is equal to x over 1. For our trigonometric ratios from algebra, what is sine from Sokatoa?
Opposite over hypotenuse.
Opposite over hypotenuse. This is x over 1. And that means we've got this third side over here, c, that we haven't defined yet. So I'm going to go ahead and define that side using Pythagorean's theorem. So Sai, back over to you. If I want to solve for that side c, what do I need to do?
C squared equals to a squared minus b, no, a squared plus b squared.
Okay, so that is
Pythagorean.
c squared equals a squared minus b squared for us right now. What is, what should I set this up as then? What's our c value? What's the hypotenuse? Oh, still at the triangle.
So
Okay, so I'm going to call this, I'll call this side z, maybe, if that helps. So how can I set up the equation?
z squared is equals to equals to 1 squared plus x squared. Is it?
So in this case, Pythagorean's theorem, your c always has to be your hypotenuse, which for us is going to be the 1 value. So setting this up again, this could be, get rid of this dot here. Okay, this could be something like this. So 1 squared is equal to what?
Okay. And
We're still at Pythagorean's theorem.
x squared plus y squared. Or
Y is an angle. There we go. C squared. Okay, so our goal is to solve for this third side z that we don't have yet. So I'm just going to take this equation and solve for z. What's going to happen? Okay, I've got one new person that just joined, but I'm not sure if that's Nikolai or Nani.
Hello, it's me. Sorry, I didn't realize that.
That's okay. Hi, Nani. So can you solve for z for us?
Which one?
So right now I've got, zoom in here just a little bit. 1 squared equals x squared plus z squared. Can you solve for z?
Z. Is it 1 squared minus x? Z equals, no, z squared equals 1 squared minus x squared.
Okay, that works. And then solve for z, one more step.
Square.
Okay.
Square root.
Okay.
Uh, 1 squared minus x squared.
All right. So now that I know what z is, so I'm going to go ahead and replace that here with root 1 minus x squared. I can go back and solve for the cosine. So what is the cosine of our y value right now, if y is this angle? I am back to the top of the order, so we are back to, oh wait, I skipped Jade. So let me go to Jade. Jade, what is the cosine of y?
Cosine of y. Resistance over jet.
Okay, so we've got our right triangle relationship here. The cosine of our angle should be adjacent over hypotenuse. So what will the cosine be?
Jet.
I couldn't quite make that out. I'm sorry. Say it one more time.
Jet.
Okay, I think you mean square root. I'm not sure. So cosine of y would be the adjacent over hypotenuse. This is root what? Jade, what should I write? Chat. Oh, I see. Okay, so she's typing in chat. Maybe. Okay, so after she's got this, I'll jump over to InV after Jade. Once we know what the cosine of y is, I'll need to substitute that back into our equation here and solve for dy over dx. Yes, so the cosine of y is 1 minus x squared underneath that square root, or this. There we go. Okay, so using this line here, I can substitute back for the cosine of y. And in B, we're over to you. So I'm going to take this line that we had previously and resubstitute for the cosine of y. What's going to happen?
Root 1 minus x squared times dy over dx equals 1.
Okay, so what is dy over dx?
1 over root 1 minus x squared.
Perfect. And then with chain rule, I could say that dy then would be equal to dx over root 1 minus x squared. So what that means is if we derive arc sine, I should get 1 over root 1 minus x squared. Okay, I'm going to do the same thing for 2 more trig functions, for arc secant and for arc tangent, and then we'll come back to a couple of these. So starting with Maxin, it looks like. Maxin, so I've got if y is equal to the arc secant of x, what can I do? Can you guys still see if I leave it as the whole page?
Yes.
Okay, cool. Then I'm going to leave it like this. So what should I do first?
Secant y equals to x.
Perfect. Secant y is equal to x. I think you had this last time, so I'm going to jump to somebody else for the next step. But this is over to, I've got sine x actually. So psi. What happens if I derive the secant of y?
Wait for a minute, please.
Go for it.
Not a minute, but oh, secant x and no, secant y tangent y is equals to 1.
We're super close. I do have chain rule though, so this should be secant y tangent y
dy over dx.
dy over dx. Perfect. Is equal to
Okay,
dx over
so
dx,
1.
which is 1.
1. Yes.
Awesome. Okay, then I'm going to jump over to, I need Nani next. Nani, what we're going to do is we're going to draw a right triangle relationship using this line. The secant of some angle y should equal to x over 1. So I'm going to draw a right triangle relationship. You can tell me which of these side lengths I need to set equal to what. So this is my angle y on this side of a right triangle relationship. I'm going to call this side A, side B, and side C. And if the secant of this angle y is equal to x, which side lengths do we know?
Are we trying to figure out the x?
So for right now, I'm just trying to draw the relationship in a right triangle. So for example, SOHCAHTOA up here for the last one, we said the sine of y was equal to x, and we use that to construct this triangle. If the sine of an angle y is equal to x over 1, because sine is opposite over hypotenuse. If sine is x over 1, then this should be the opposite side for x, and the hypotenuse needs to be 1. Okay, for
we have
our problem here,
secant. So it's 1 over sine, is it?
secant is 1 over cosine.
Oh, right, okay, 1 over cosine. So it's cosine is opposite over.
So this is SOHCAHTOA.
Well, adjacent over h, so it will be 1 over a over c.
Okay, so cosine would normally be a over c. So what will secant be?
Secant b.
What will
Oh.
secant become?
Isn't it 1 over cosine?
Yes, so instead of adjacent over hypotenuse, what will secant become?
C over a.
C over a, perfect. So we can say, let me write out what we just did. So we said the cosine of some angle theta was equal to adjacent over hypotenuse. But also that secant is equal to 1 over the cosine. So therefore, this would be 1 over adjacent over hypotenuse, or hypotenuse over adjacent. Okay, the secant of our angle, y, was equal to x. So right now we know our hypotenuse over adjacent is equal to x over 1. So what is C and what is A? Back to Nani, and then we'll jump to the next person for the next part.
What is C?
Yep, so we need side lengths for C and A for our triangle.
Is C dx?
Okay, so C is the hypotenuse, is x, so I'm going to replace this here. X. And what is this side length?
1.
1, perfect. Okay, jumping over to, I have, I believe that's in B next. Okay, so in B, I want to solve for this side length B. What do I have to do?
Tangent y equals.
Okay, so we can solve this without using any trigonometric ratios yet.
X squared minus 1 equals b squared.
Okay, x squared minus 1 is equal to b squared. So therefore, b is equal to the square roots of x squared minus 1. So that was all Pythagorean theorem. I'm going to move this down and add one more line for everybody else. This is Pythagorean's theorem, x squared is equal to 1 plus b squared. And then she solved for b. So given that, I can just go back and use this triangle relationship that we've just solved for to substitute for secant y and tangent y. Okay, the secant y we already know is x over 1. The tangent of y, we're going to have to rewrite though. Jade, I'm going to have you try your microphone one more time. So what is the tangent of y?
Is that B or beta? B?
This is b.
So tangent Y is B.
Okay, you're right. So tangent y would be opposite over adjacent, which is b over 1, or just b. Which is the square root of x squared minus 1. And that's going to allow us to substitute for all of these. So I'm going to max in next. Max in, going back to this line here in red. I need to make substitutions and then solve for dy over dx.
Okay. Should be x over square root of x squared minus 1.
We're close. So this is the secant y times the tangent y. Secant y is x over 1. Tangent y is root
Yeah.
x. So what should this be?
Oh, x times square root of x squared minus 1 all over 1.
Okay.
Oh, that's it. Right. Times dy over dx equals to 1.
All right. And last step, solve for dy over dx.
Dy over dx equals to 1 over x times square root of x squared minus 1.
Awesome. And then because our derivative of y would be the derivative of the original function, which was arcsecant x. The derivative of arcsecant x is equal to this. If there's chain rule, then this would be a dx on top. We'll go ahead and add that to the other one too for a general form. Oh, I already did. Okay. So if there's chain rule, we'd have a dx on top. Last one. We'll do arctangent. So y is equal to the arctangent of x. And we are starting with psi this time. So psi, what's our first step?
Derive it. So
We don't know the derivative of arctangent yet, so we're gonna have to cheat and do something else first.
Wait a minute.
I'm gonna scroll up to the last one really quick. So we had y is equal to the arcsecant of x. So we undid the inverse secant.
Yes. So tangent y is equals to x.
Okay, and now I'm gonna stick with you for one more step. So what can we do now?
Derive.
Perfect. What's the derivative of tangent y?
tangent secant square
So I've got
y
this. Sorry, go ahead.
dy dy over dx is equals to 1.
Okay, try to throw parentheses in here so now that's the end of the angle, but you're right. So dy over dx is equal to 1. All right. I'm going to do the same thing again, and we're going to create a new right triangle relationship over here. Shapes in this. Okay, that's much better. So I've got our right triangle here with an angle that is y. And I'm also going to have 2 side lengths. We are over to Nani next. Nani, actually, I think I had to do this last time, so I'm going to skip. And we'll go over to NB. NB, if the tangent of y is equal to x, then which sides do I know?
B and C.
Not B and C, no. For SOHCAHTOA, what is tangent?
Opposite of adjacent.
Okay, so this is really which over which? Which side lengths do we know? You said tangent is opposite over adjacent. We know the tangent is x right now. So I'm going to turn this into a fraction. This will be x over 1. So if the tangent is x over 1, then which of these side lengths can I update on the triangle? B? Okay, what is B?
X.
Okay, and we know one more side.
A.
Okay, A is what?
1.
Awesome. So I can step in again and we'll solve for C. I'm going to jump over to, I've got Jade next, I believe. Jade, what is C?
X squared plus 1.
I could say C squared is x squared plus 1. So therefore, what is C?
Square root of x squared plus 1.
Awesome. Okay, so now I know what C is. So I'm going to go back and we'll make some substitutions for this secant. Okay, I'll just have to draw this back up, I guess. There we go. All right, so the tangent y was x over 1. The secant of y, though, secant is our hypotenuse over adjacent. So what is the secant of y in this case? I'm going to go to psi. Psi, what is the secant of y?
So mm, uh so okay. X over 1. Oh, sorry. Opposite over. um. Hypotenuse over opposite.
Really close. So cosine is adjacent over hypotenuse. So if I flip it, it'll be hypotenuse over adjacent.
Yes, sorry. Yes, hypotenuse over adjacent.
Okay,
So-
so for this, what will hypotenuse over adjacent become?
C over C over 1.
C over 1, perfect. This is the square root of x squared plus 1, all over 1. So I'm just going to write like that. Okay, so that brings me back to, I'm going to go to Nani next. Nani, so the secant of y is square root x squared plus 1. Going back to our previous line, the secant squared of y times dy over dx is equal to 1. After we make our substitutions, what will this line become?
Do we equal them?
I'm going to make a substitution. So we know the secant of y is square root x squared plus 1.
So x squared plus 1 square root of x squared plus 1 squared. So that takes the square root out. So
Right, so that's just x squared plus 1.
y and dy over dx.
Okay, so the whole secant of y was our square root, so I won't have any y's left.
So dy over dx
Okay,
is equals to 1.
awesome. And last step, solve for dy over dx.
Okay. Do we substitute?
We've already substituted, so the goal is to just get dy over dx alone on the left side.
Oh, okay. So it's 1 minus.
Not minus, no. Right now we're multiplying, so how can we undo it?
Oh, it's multiplying, so it's 1 divided by x squared plus 1.
All right, that's good. That is the derivative of our original y value. Our original y value was the arctangent of x. So we can say that the derivative of the arctangent of x is equal to this. 1 over x squared plus 1, or if we have chain rule, dx over x squared plus 1. Okay, so putting them all together. We've got 3 rules. I'm gonna leave this open for a second or two, just so everyone can take a screenshot. And I'll go through a bunch of sample questions and start calling on people. So give it a moment. And all right. So let's say y is equal to the arc sine of natural log x. I want to be able to derive this in terms of x. So I'm going to start with NB. NB, what happens if I derive right now?
Mm. EX over
We're close. What's the derivative of natural log x?
e to the power of x.
Not quite. I'm going to phone a friend. Maxon, what's the derivative of ln x?
1 over x.
1 over x. Okay. Then NB back over to you. So I've got 1 over x on top. Which I'm just going to pull out a fraction entirely for now. So I've got 1 over x times 1 over something. So on the bottom part now. What should I write?
Root 1 minus ln x squared.
Perfect. Okay, so really I've got this 1 over x on top here. But if I pull this out, then I can end up moving that to the bottom. And it will look like this. Any questions? First example. I'm gonna try another.
No.
Let's do the arc secant of 4 raised to the x power. Let's see, I'm on Jade next. Jade, what do you think is going to happen?
Four to the x ln 4 over x square root of, no. 4 to the x square root of 4 to the x square minus 1.
Awesome. We could do some simplifying there if we really wanted to. Our 4 to the x's could cancel. And and then 4 to the x times 4 to the x. If I'm multiplying with the same base, we can add the exponents together. It'd be 4 to the 2x. But I'm going to go ahead and leave it like that for now. Any questions on our derivative for this one?
No.
Okay, I'm going to see if I can add an extra line to this table here so that we can have everything together. Okay, so that brings us to this one. Let's do the arctangent of we'll do e to the 2x. Just in Jade. Okay, so we're on Maxon next. Maxon, what's going to happen here?
One over, oh, sorry, no. E to the power of 2x.
Chain rule.
Two.
There we go.
Over 2, e to the 2x squared. E to the power of 2x squared plus 1.
Awesome. What is e to the 2x times e to the 2x?
E to the 4x.
That's it. So I could simplify this as e to the 4x if I wanted to. And we've got a couple examples. All right. I think that's about it for new stuff. Does anyone who is joining late have any questions on the homework? Flash that up again here too. We had a bunch of derivative rules and integral rules.
Can we try the first question?
Okay, this one for number 6.
Hmm.
Okay, so if f of x is x, what's the derivative? So what happens when I derive x?
It becomes 1.
1. So I've got right now f prime at any x value is equal to 1. So if I plug in 5, I don't have any inputs for my function, and this will still be 1.
Oh. Okay.
See if I've got any arctangent stuff here. Gosh, I might have pulled out the arctangent stuff actually. Oh, no, I didn't. Here we go. So there's an arc sine of 2x. So if I derive the arc sine of 2x, let's see, I'm on sine x. Sai, what's going to happen if I derive the arc sine of 2x?
Is it on formula sheet?
Yes, this is the new formula for
Oh.
today. I'll flash this one really quick.
Okay.
If I derive the arc
okay.
sine of x, we get dx over square root 1 minus x squared.
Yeah.
So if we derive the arc sine of 2x, what should happen?
So, okay. 2 over root 1 minus 2 squared? Is it?
This should be root 1 minus, this should be everything that was in the angle squared.
Square. 1 minus 2 squared? Or 2x squared?
So this would be 2x squared.
Okay.
Okay, so which of these match?
D?
D matches, perfect. I'm going to copy this into the other program, I think, because that's a little bit easier for me to write in.
Mr. Brandon, I have a question.
Nani, you go for it.
D says 1 minus 4x squared.
Yes, so we had
2x.
Yep, 2x times 2x. So the 2 times 2 is 4. The x times x is x squared.
X squared. Okay, I see. Sorry.
No, you're okay. So jumping down to this one then. So we've got y is equal to the arctangent of cosine x. I'm going to jump to, okay, we're back around again. So in B, if y is equal to the arctangent of cosine x, then what happens when we derive? Grab our formulas again.
Negative sine x over cosine x squared plus 1.
Okay. So which one? Yes. Okay, I think those were the harder ones. go ahead and we'll try this last one together. Okay, going over to Jade next. I have f and g are differentiable functions, and we've got a couple derivatives of f and g at 1, the actual values of f and g at 1, and the derivatives of f and g at 2. I want to know if we have another function h, which is the composite function f of g of x, then what would h prime at 1 be? So first, let's get a general form for h prime at x.
So f prime gx plus f prime gx, times g prime x.
Okay, so that is chain rule. And then our goal was to get this at the value 1. So we can make some substitutions. So h prime at 1 would be f prime of g at 1 times g prime at 1. Okay, Jade, sticking with you. What do I do next?
So it will be f prime 2.
Okay,
G1 is 2 and times minus 3.
perfect. What is f prime at 2?
Minus 4.
Okay, so we can make another substitution. And what's our final answer?
12.
12. Any questions on this one?
Sorry, how can we get 2 for third equation?
For the third equation, 1, 2, 3.
Sorry. There's it's provided, right?
So we've got six functions provided here. Since we plugged in g at 1, which was 2. So if I substitute, and then this will be f prime at 2.
Okay. So g prime 1 is 2. Oh, -3. Okay, I got it. Thank
Cool.
you.
Yeah, no problem. All right, so let's do. This is just more advanced chain rule stuff. I'm going to skip that for now. So we had some integration stuff as well. Okay, I'm just looking for the hardest stuff here for the sake of time. Maybe this one. Okay, so I've pulled all of these questions from previous year's AP exams. This one, I've got the derivative is the tangent of x. I want to know what the original function would be. We do have all the math that we need to actually work this out as an integral. But because this is multiple choice, we could just derive all of the answers instead. So I'm gonna leave that up to you guys to decide how you guys want to solve this. We are over to either InB or Maxim next. I can't remember. So I'm gonna jump to InB. So in B, I've got options. We can either derive all of these answers and figure out which one gives us the right derivative, or we can integrate and work this out. And what do you prefer?
Integrate.
Integrate, okay. I like it. So we're going to integrate the tangent of x. Now, I don't think we've got a formula for integrating tangent x yet. So I'm going to make a substitution here. The tangent x is the same thing as what function over what function?
Sine x over cosine x.
Perfect. And then we can solve this using use substitution. So with use substitution, let's say u is equal to the cosine of x. Then what is u prime?
Negative sine x.
Okay. Why did I choose u to be cosine x? Anyone?
Hmm.
So when we're working backwards with integration, our first step needs to be to divide by u prime, which means my u prime would have to be on the top of the function. So if I chose u to be sine, my derivative would be cosine, and I don't have a cosine on the top. So in order to make this work, my u would have to be cosine. So I'm rewriting this with u substitution now. This is the integral of, I have a positive sign, I need a negative sign. So in B again, what can I do?
Negative. U prime.
Okay, that's it. I'm going to write this out as a separate step though. So this is negative sine x over cosine x. So I haven't changed anything, but what that allows us to do, what that allows us to do is to substitute directly for u prime. I needed a negative sine x on top. So in order to do that, I multiplied by -1 twice. That does not change my original problem. It gives me the -1 we need to do our substitution. That gives us this, which NB was about to say, I think. So this is u prime over what?
U.
U, perfect. And last step, what happens if I integrate u prime over u?
U prime times u to the -1.
Ln u.
Okay, so Nani, you're right. I could rewrite this as u to the -1 times u prime. But when I go to integrate that, I can't integrate using power rule because when I go to add 1 and then divide by the new power, I'll end up dividing by 0. So this is actually a special case. If I integrate dx over x, I'll get the natural log of x. If I integrate u prime over u, I'll get the natural log of u. Okay, and then plus c because we're integrating indefinitely. And the last step, I can substitute for u. So this is negative natural log of, what should this be?
Cosine x plus c.
Perfect. Now, technically, we've got absolute values in all of these answers here that involve the natural logs. And the reason why is because we cannot take the natural log of 0 or a negative number. But we do match. So which answer is correct?
Is it D?
It is D. Okay, I think that's all of the trickier ones from the homework. So I'm gonna go ahead and stop us here. and we'll bring in a couple of the physics students in about 20 minutes or so. So we still have a little bit of time. If you guys have more questions on the homework that you want me to answer, I'll just open it up for those. If you guys want to leave, all these sections are optional, so you can leave at any time, but feel free to leave. So does anyone have any last minute questions?
Can we do like one more problem or like two?
We can do a couple more problems. Do you have any numbers that you weren't sure on?
I think anything is okay.
Anything is okay. Let me call out topics really quick. So these two are integration by parts. That one's just indefinite integration. This one's same idea as what we did last time. U substitution, U substitution, U substitution.
Not
Substitution
the
again.
Maybe the sine cosine.
Okay, so the integration by parts one.
Yeah.
Okay, I'm gonna have you pick one. So top or bottom?
Both. But we can
Okay, I've only
bottom.
got 2 questions from the homework on that topic, so I think I'm only gonna do one, but
Bottom.
okay, bottom.
Bottom.
Sounds good.
Mhm.
If we need another, I'll create another.
Okay.
Here we go. Okay, second derivative is given by, oh, this isn't actually integration by parts. Look, this is just integration twice. That's right. So I'm gonna integrate this twice since this is the second derivative. So over to, we'll start with Nani first. What happens if I integrate the 2x?
Two. Okay.
That would be the derivative, I think.
Sorry. 2x over 2x squared over 2.
Okay, 2x squared over 2. And then if I integrate cosine, what do I get?
Integrate cosine, you get sine. Negative.
So I would get a positive sign if I integrate
yeah.
positive cosine. I just had that negative sign already here from the original function, so I'm just going to leave that negative here. Okay, so this is prime x.
We need to integrate it again, right?
Yes, we do. So we need to solve for f. Okay, I'm going to jump to the next person, which is Sai. And so Sai, what's going to happen if I integrate this one more time?
2x cubed divided by 6
Okay.
minus
If I integrate sine?
cosine? Negative cosine?
Negative cosine. And if I integrate a constant?
C.
C times?
Square? Huh? 2c.
So if this had been 3, what would happen when you integrate 3?
1. Huh? Integrate 3?
Help you out. So right now there's no x's here. So this is really cx to the 0 power.
Okay, cx. Okay.
Right, cx to the first power. Okay, and then plus I would have a new constant, so I'm gonna call that d, I guess.
D. Okay. I see. Okay.
Okay,
Just
so
constant.
something like this. I'm gonna simplify, and this should be f of x is equal to my 2 and my 6 can cancel. I'm left with x cubed over 3 plus the cosine of x, since I've got a minus and negative, plus some constant x that we don't know what the constant is, plus another constant. Which of these answers could be f of x?
A.
Okay, A is the only one that works because it's got the right sign in front of the cosine. Since these constants could be any number, it's possible for these constants to be negative numbers. So it's okay that this is subtracting an x value, since C could be -1.
So the answer can be A, right?
Yes, A is the only one that could fit. Since I have to have x cubed over 3, C and D cannot be true. And then I have to have a plus cosine, where B has a minus cosine.
Okay.
All right, I'm gonna give us one more. So this is I want to integrate x times the natural log of x in terms of x. So this is integration by parts. Does anyone remember the formula?
No.
Okay, so if I integrate uv prime, I'll get uv minus the integral of u prime v.
Oh.
And we get that from product rule actually. So if I was to derive uv, I would get u prime v plus uv prime. So if I was going to integrate both of these sides, the integral of the derivative of uv can cancel. So I'll be left with uv on the left side. Since I'm adding and integration is repeated addition, I can break this apart into two separate integrals. This would be the integral of u prime v plus the integral of uv prime. So if I want to solve for the integral of uv prime, then I can subtract this integral from both sides. That will give me uv minus the integral of u prime v is equal to the integral of uv prime, which gives us integration by parts. Okay, zooming back out. So really, this formula is just product rule. And the integral of uv prime is equal to uv minus the integral of u prime v. Okay, so with that in mind, I've got x and ln x. We have a priority order, I late, for determining which is the part that we need to derive, which would be our u. So I'm going to start with just finished size. This should be Jade. Jade, which of these should be u, x or natural log x?
Natural log of x.
Right, so an I late, so logarithms come before algebraic functions, which would be our polynomials. So for this one, u is ln x, therefore u prime is what?
1 over x.
I'm going to write dx over x, but you're right. So I am out of space. Okay. Then I'm also going to have a v and a v prime. Okay, so v prime is the part that we need to integrate. So what's left of our original function?
X.
X. If I integrate x, what do I get?
X squared over 2.
All right. So I'm going to plug that into our formula, and we can finish this off. I'm going to jump over to in B. So in B, plugging that into our formula, what is the integral of x ln x?
Ln x times x squared over 2 minus
Okay, you're right. I'm just having some issues typing that, so I'm gonna move this over here. Okay, ln x times x squared over 2.
integration of dx over x times x squared over 2.
Awesome. And so that's going to allow us to do some stuff with this last integral. Maxine, is there anything that I can cancel or do with this part?
Well, Maxon's browser crashed. He's not in anymore.
Okay, so I'm going to jump to Nani then. Nani, is there anything that can cancel?
Dx over x.
Okay, so what should this become?
X squared over 2.
Okay, I've got an x squared here on top and I've got an x on bottom. So if I cancel these, what's left?
Cancel which one?
Right now I've got x squared dx on top and I have 2x on bottom. What can cancel?
Dx.
I don't have a dx on bottom.
I mean the x.
I can cancel 1x. Okay, so if I cancel 1x from the bottom and 1x from the top, I'll be left with x over 2 dx. Okay, what happens if I integrate x over 2?
What happens when
I need to integrate x over 2.
x over 4? No, x2 over 4?
X squared over 4.
Yeah, sorry, x squared over 4.
That's okay. And then I've got a constant of integration here since that was our last integral that we did. So that leaves us with our answer. If I integrate x ln x, I'll get x squared ln x over 2 minus x squared over 4 plus c. All right, I think I'm going to stop there. If you guys have more questions as you guys are working through the homework, please hit me up either on Teams or on WeChat. I've got about 4 minutes before I need to hit the time that the next class voted on. So I need to change classes, unfortunately. But thank you so much for coming. I know it's really hard to get people here over the summer.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
Goodbye.
Goodbye.
Sorry. Sorry. Hello. Can you hear me?
Hello. Yes, I can.
Awesome. Okay. Still having pen issues, but so a couple things before I get started. We've got a new website that I sent over on Teams a while ago.
Yes.
Were you able to register?
Yes, I did, and I turned in my homework with the
Awesome.
with this new website.
Okay, so let me go check on that really quick. I think Maxon crashed in the middle of last time, so let me go remove him here too. Okay, cool. Okay, surveys and projects. Awesome. Okay. So that was a lot of reading.
Yeah.
This first one was mostly just like measurement, unit conversion stuff. Were there any questions that you had from any of the readings?
Oh. Uh. No, I don't think so.
Okay. So I'll go ahead and grade your stuff at some point, either tomorrow or the day after.
Okay.
And then I need to upload your next assignment there as well. So I'll do that after we break from this class. But I think should already be up from whenever we sent this to Brian, and then on Teams before it closed. Okay, so I'll send a picture of this, but I'm still kind of following this for now.
Okay.
So you know what's coming up. And were there any problems with the new website as far as registering or anything goes?
No, not really.
Considering this over course sites, because course sites is going to, course sites is ending its services in August. So I won't be able to use it for next year. So I've been shopping around for new platforms.
Okay.
All right, so next stuff is vectors, dot products, cross products, which I think we've already gone over in class.
Oh, I don't really remember it though.
Don't really remember stuff. Okay, so let me jump into some of that then. Do I have this one? Okay, I might not have it locally, but I'm pretty sure I've uploaded here already too. So this is, okay, under physics, under pages and PowerPoint. So we got a bunch of stuff that I was planning on using. So I'm gonna jump over to vectors for the next one.
What chapter is it?
Don't.
Oh, chapter 2.
Yep, so this is chapter 2 under PowerPoints.
I got it.
Cool.
Yeah.
Nope, that's wrong screen. Okay, I think I'm just going to show on this so they can draw on stuff as well. But so when we're talking about vectors, and we've got scalar quantities and we have vector quantities, scalars are anything that does not have direction. So that could be speed or age or heat or distance. All don't have a direction associated with them, just a magnitude. And so scalars are just a value with units.
Okay.
Versus a vector does have direction. So if we start talking about velocity, then the direction matters. So this is the same thing that we saw in Calc 2. We were talking about displacement versus distance traveled. Your total distance traveled is a scalar quantity because we don't have direction, but your displacement is a vector quantity because it had both magnitude and direction. So the same rules that we just used for Calc 2 are also going to apply.
Oh, okay.
Where we'll need to, if we're talking 2 dimensions, worry about the signs when we go to add stuff together whenever we're talking about a vector, but not necessarily worry about the signs if we're talking about a scalar quantity.
Okay.
So vectors in physics are typically shown using an arrow above the symbol. So when it's printed, it looks like this. But when you are writing, it looks like this. So vector x might look like that. So it's a little bit of a hat that kind of curves up at the end. But if you see any of those, then that's a vector.
Okay.
Other ways that we could write it, I zoom way in here. If you see the absolute value signs over the vector, so that means they're looking for the magnitude of the vector, which means we don't care about the direction anymore. So I could say that for this vector A at a 45-degree angle above the horizontal of 1 foot worth of displacement. This looks like a fly to me, but this house fly traveled 1 foot at a 45-degree angle above the horizontal. So I could say that its horizontal displacement was 1 times the cosine of 45, and its vertical displacement was 1 times the sine of 45, which both ends up being root 2 over 2. The magnitude of the vector, though, is 1. Any questions on terminology, vocab?
I think it's okay.
Cool.
I'm okay with
Polar equations. We did a little bit with polar equations in Calc 2.
it. Yes.
So our polar equations are another way of writing our angle using unit circle values. So in this case, we've got a magnitude and we've got a direction that's given as an angle, the same way that the unit circle is given. So that's starting, if you want to think about this as a compass, then you're starting in an east direction. And you're always giving a degree that you are going counterclockwise of east. So I could say that this is 12 newtons at 210 degrees, which in polar, that's all I need in order to know exactly which direction this force is actually going.
For polar equation, is the degrees always start from the on the x-axis from the right?
Yes.
Oh, okay.
So it's the same way that the unit circle works. So you're starting where 0 would be on the unit circle, and you're moving as you would for an angle on the unit circle.
Okay.
Just we can do any decimal that we want, so we're not limited to just pi6 or pi4 anymore. Depending on what profession you are, some professions prefer to use degrees, some professions prefer to use radians. Most of the stuff that we will do in this class is going to end up being in degrees. Even though if you do want to be a mechanical engineer, down the line eventually you'll turn to radians. Just because everything cancels when you start using radians, kind of like we saw in Calc 2. However, there are a lot of professions that prefer to use degrees, mostly things that are involved in navigation, because you already have degrees on a compass. So if you're a pilot or if you're the captain of a ship, you're going to report your direction in terms of a compass instead. So it would be something like 30 degrees north of west. So that would be something like this. I've got a compass, so north, south, east, and west. I'm going to start here going west, and then move 30 degrees to the north from where west was. Okay, and I would write this as, well, I would say this as 30 degrees north of west. For pilots, we also talk about being above or below the horizontal. So if I've got a plane, we've got a horizontal here that is parallel to the surface. If I want to talk about my angle of attack, so let's say this airplane is not perfectly on the horizontal, but we are 4 degrees above the horizontal. Then that's how I would report it.
Oh, okay.
But everything has to have a reference. So I'd say we're flying 30 degrees north of west at a 4-degree angle above the horizontal, or with an angle of attack of 44 degrees.
Okay.
Okay. So scalar multiplication is one way that we could multiply vectors together. It's really easy. It's just multiplying the magnitude of the vector by another number, and this makes it bigger or smaller. So if I have vector A here in this direction, and I want to double it, then I could do 2A, which is scalar multiplication, just doubles the magnitude of the vector without changing the direction at all. So scalar multiplication is when you multiply by a constant and you're not changing the direction.
Oh, okay.
Okay, we have 2 separate types. I'm going to come back to vector notation in a second. We have 2 separate types of vector multiplication. So there is, I've already got vector components on all of these actually. Okay, maybe I do need to go back and actually do vector components first. Sorry.
Okay. It's okay.
So unit vector notation. In 2 dimensions, unit vector notation is the IJ definition of a vector in your math textbooks. All this means is we've broken it down into horizontal and vertical components. So this vector A moved 4 units in the x direction and 3 units in the y direction to have a total magnitude of 5 units, right? Its horizontal component would be its I component. So I could say that I could define this vector as 4i, 3j. Because I've defined the vector in terms of its horizontal and vertical components, I already know the direction as well.
Okay.
This is useful when we're talking about forces, especially because a lot of times forces will only act horizontally or vertically. So for example, if this is the force that you are pulling on a box with a rope in this direction, you're pulling with a total of 5 newtons of force. But assuming that this 3 newtons of force that's acting vertically is not enough to counteract the force of gravity, then the only component of that 5 Newton force that's actually going to affect the box's movement is going to be the horizontal component of that force.
Okay.
In 3 dimensions, we add a k to this. So this would be your I, j, k definition of a vector. So starting from the point of origin, I is how much you've gone on the x-axis, j is how much you've gone on the y-axis, and then k is how much you've gone on the z-axis.
Okay.
I'm gonna see if I can draw that really quick. Insert a graph really. Okay, so here I've got a 3-dimensional graph.
Yes.
So this is going to be my, call this my z-axis, x and y. So with my ijk definition, I would get something like this. So if I wanted to graph a vector of 1, 2, 3 in my ijk definition, I would do this. So go over 1 for x, 2 for y, and then back 3 for z. So over 1, up 2, back 3. 1, 2, 3. I'm going to go to this point. Really don't like the way that turned out, so I'm going to see if I can do that again really quick in GeoGebra. I want to graph the vector 1, 2, 3. Will that work?
Oh.
Maybe not. Y is equal to 1, 2, 3. Okay, there we go.
Oh.
Okay, so what we've just done, and label axes, tools. Nope. Settings maybe. So axes. Okay, cool. So if I flip this up on its top, so we can see what's happening 2-dimensionally. Here's my x and y axis. So this is 1, 2, 3 for my vector. For the ij definition, I went 1 and then back 2 for the y axis, right?
Yeah.
But then if I flip this up again, you can see for the z-axis, we went up 3, 1, 2, 3 in order to get to my point. And that gives us a 3-dimensional vector. Especially when we are adding vectors together. So if I wanted to add the vector 1, 2, 3 to the vector 1, 1, 1. So at the origin, this is what 1, 1, 1 looks like.
Mhm.
Vector in 3D space here. But what I would really be wanting to do is to shift this up, which I'm actually not sure how to do on this, so that it went tip to tail, right?
Yeah.
So by adding these together, I would end up with a vector that did this. So I can add my x values together. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. And I would get my new result of what would happen. This color. Oh wait, position, starting point. Oh, there we go. Okay, let's try that for this one. Okay, so here in red, I've got what the result of adding these two vectors should be.
Yes.
And I would get that if I took this vector here in green and changed its starting position to 1, 2, 3, hopefully. Awesome.
Oh, okay.
Okay, so adding vectors, we could add them tip to tail. It is much, much easier once we start talking 3 dimensions to add a bunch of these vectors together if we've broken them down into their I, J, K components, which is really just your X, Y, and Z components. Any questions on component definitions?
Oh, no. I'm okay.
Cool. All right. So if you see IJK, that's all it means. So for vector addition, as long as your vectors are moving the exact same direction, we can just add them together. However, if our vectors are moving in the opposite direction, we'll need to subtract them instead. If our 2 vectors are not perfectly on the same line, then adding them together would mean adding their component vectors first, and then creating a resultant vector. With the sum of our horizontal and the sum of our vertical components, we could then use Pythagorean's theorem to solve for the magnitude and arctangent to solve for the angle.
Okay.
So that would look something like this. Here I've got two vectors that I want to add together. So this is 95 kilometers traveling east and 55 kilometers traveling north. If I want to add them together, I would add them tip to tail. So I'd add all of my horizontal components. The total sum of my horizontal is 95. The total sum of my vertical is 55 because there was no horizontal component of 55 kilometers north and there was no vertical component of 95 kilometers east. So once I've got the sum of the horizontal and vertical components, I can use Pythagorean's theorem. 95 squared plus 55 squared equals c squared. Solve for c. And then I'll get 109.8 kilometers. If I want to solve for the angle, then I can use my inverse tangent. If I use inverse tangent, I end up getting 30 degrees exactly. On your AP exam, if you have an option, this would be much, much easier to just write as a unit vector instead, because then you don't have to do Pythagorean theorem and you don't have to do the inverse tangent. So if you've got an option of defining your vector, then I would recommend defining your vectors as component vectors if you're adding a bunch of vectors together.
Okay.
Just because it saves time. But if they ask you specifically for what's the magnitude of the resultant vector or what's the angle, then we do need to go back and do all that.
Okay.
All right, so here's a bear that's walking a bunch of different directions and distances. If I want to figure out what the bear's displacement is, that would be their distance from the start point, which would look like this line. And so to do that, what I'm going to do is I'm going to sum up all of my horizontal components. That's 35 minus 12 is going to give me this distance of our triangle of 23. And I went up 20, down 6. I've got this distance of 14. And I can then just define as a unit vector definition and be done if they just ask for displacement.
Oh, okay.
If they ask for displacement in meters, then I need to go back and do Pythagorean's theorem as well to actually calculate how many meters away that was. And if they ask for the angle, I can give that too.
Okay.
So if they just say, give me the displacement vector, then I can say 23i 14j meters.
That's the displacement, right?
Yep, so that's my displacement vector.
Oh, okay.
If they ask me for the displacement, Then I need to go in and say it's 26.93 meters at 31.3 degrees above the horizontal.
Okay.
Because displacement also requires direction, and we're working in more than just the two-dimensional analysis now, like we did in Calc 2, I do need to include my angle.
Okay.
All right, all of this I know we've done in calculus and pre-calculus. I'm going to skip for now. The only new stuff is we're defining stuff as a unit vector, which I know you can do. Okay, I'm going to slow down here for English again, but 32 degrees south of east means start east and go 32 degrees towards the south. So here's east. I'm going to take that and swing 32 degrees towards the south, and that gives me my direction.
Okay.
All right, and the stuff I really want to talk about. So scalar multiplication just means we multiply the magnitude of the vector by some constant, right?
Yes.
But if I have vector multiplication, there's actually two different types of vector multiplication. And we use two different symbols to denote them in physics classes and afterwards. So the first is what we call a dot product. A dot product tells us the magnitude of the vector that's acting in the same direction as our current vector. Or the magnitude of the vector that's acting parallel to our second vector. So in order to find that out, we'll be using the cosine of the angle between the two vectors. So I'm going to zoom in here because these symbols look a little bit similar, but this is actually phi as a Greek letter versus theta. So I've got theta 1, theta 2, and phi being the vectors angle difference. So the angle difference here is really theta 2.
Okay.
Oh, sorry.
Oh.
It is not. Theta 2, I think that actually does go to the horizontal. Never mind, sorry. So theta 2 minus theta 1 would be phi
Okay.
on our picture here. Okay, so in order to figure out what component of B is acting parallel to A, then I would have to do B cosine of phi, which is the cosine of theta 2 minus theta 1. If I want to multiply them together, then I can take the magnitude of A and multiply by the component of that second vector that's acting parallel, which would give me what we call the dot product. So that dot product, A dot B, would be A times B cosine phi.
Okay.
All right, so here's what it looks like. If you know what these vectors are, this is a continuation of the last one, I think. Okay, so I've got a magnitude of A of 12 at an angle of 30 degrees and a magnitude of B of 5 at an angle of 65 degrees. So if I want to do A dot B, this will be the magnitude of A, 12, times the magnitude of B, 5, times the cosine of the difference in our angle, which would be phi, or 65 minus 30 is 35. So that
Okay.
gives me 60 cosine 35, or 49.15. In our unit vector notation, though, our dot product will end up multiplying all of the individual components together. So our dot product would look like this. Our x values multiplied together plus our y values multiplied together, plus our z values from 3 dimensions multiplied together. Okay, here's what that looks like. So I've got two different vectors here, and there are I, J, K definitions. These are 3-dimensional vectors. If I end up multiplying A dot B, then I'll end up summing these together like this. So this will be 3 times 2 plus -4 times 7 plus -5 times 3, which gives me -37. Okay, this dot product is telling me the additional vector that will result when we take the two dot products together. Let's see if I can draw this really quick in our other program. Move this off to the side so I can see what we're actually drawing. Okay, so I've got two vectors that were given. So this was 3 u equals 3, -4, -5. And the second vector of 2, 7, 3. Okay, so two vectors in 3D space, right?
Yes.
Okay, I'm gonna recolor these really quick as red and green. Actually, it's kind of hard to see with our axis being red, green, and blue. Okay, anything that's not red, green, and blue. Let's do pink and do this purple. All right, so I've got two different vectors here in 3D space. Now, with any two vectors in 3D space, it is possible to find a third vector that would end up being perpendicular to both. So, for example, this purple vector that I have here has infinitely many vectors that could be forming at a 90-degree angle here, because I could take here, I could point it like this and then draw a circle around this, and any vector that touched the circle around it would end up being at a 90-degree angle, right?
Yeah.
Cool. So then for these two vectors, because I have infinitely many vectors that could be at a 90-degree to the purple one, I could pick the one vector that is also at a 90-degree angle to this pink one, and go in that direction and end up creating a 90-degree angle with both. That vector is what we call the cross product instead. Our cross product, instead of being the part of the vector that's parallel, is going to be a resultant vector that's perpendicular to two other vectors. In 3D space, for any two vectors, you'll end up with a single cross product. I'm going to leave this open for now, and we'll go ahead and calculate what the cross product of these two vectors would be. I think I've skipped ahead. Okay, so our cross product tells us the component that would be perpendicular instead, which means if we're looking at two vectors in 2D space, this would be AB sine phi, using the same principle that we had last time. But in 3D space, this is a little bit more interesting, because our resultant vector's direction is going to be the direction that is perpendicular to both of our original two vectors. If you do that in 3D space, you'll end up with two possible vectors. The one that cross product gives can be found using our right-hand rule. I don't really like this picture actually, so I'm going to redraw it. I've got a thumb here, and I'm gonna give the rest of my hand coming out this way. Okay, so if you point your thumb in the direction of one vector, so going up, and you point your fingers in the direction of a second vector, going horizontal this way, then your palm will be pointing out of the page, right? So for the z-axis. The direction of your palm would tell you what your cross product is. If you're using your right hand. If your cross product ends up being negative, then it will go backwards. So instead of going in the direction of your palm, it will go backwards away from your palm. In terms of unit vectors, in order to find your cross product, we can start by creating a matrix of IJK definitions for both of your vectors. So for me, stealing from vector A, I've got AX, AY, AZ. Stealing from vector B, I've got BX, BY, and BZ. I'm going to have a third vector C that will end up being our cross product that has an IJ and K component. IJK.
Okay.
Okay, so I'm going to always put the IJK on the top here. And then we'll end up taking cross products. So in order to take our cross products, what we'll end up doing is something like this. So to figure out the i's, I'm going to cross j and k. So I'm going to forget about this column and just look at this one. Okay, what's left for my other two vectors would be the cross product by times az minus bz times ay. And that would tell me how much I would need to travel in the x direction. Okay, we had, copy our vectors really quick. 3, -4, -5. Um, 3, -4, -5. And we also had, move this down just a little bit. Um, 273. Okay, so starting with the cross product, first thing we do is ignore the first column, and then I'm going to cross 7 times -5 is -35. Minus 3 times -4 is -12. So that is 35 plus 12, or -23. Okay, for the j, so that's how much we're going to move in the y-axis. I'm going to do the exact same thing, except we're going to get rid of a j column instead. So ignoring our j column this time, I would have 2 times -5 minus 3 times 3. Or -10 minus 9 is -19. What do you think we'll do for the k?
We cover the k
Okay,
and we cross multiply we multiply 2 and -4
All right.
minus 3 times 7.
Okay, -23, -19, -29.
Oh,
Okay, so I'm hoping I can show you here that we are actually perpendicular to both of these, hopefully. Ah.
oh, I can see. Oh, yes, I can see.
Okay,
Uh,
so we are currently perpendicular here to the purple one.
yeah.
And hopefully if I zoom around. Ah,
Oh,
ah,
oh.
having a hard time with this, but we should be perpendicular to both of them.
Yeah, okay.
Um, okay, here's two more. So these are a little smaller. I'm going to try graphing these two as well. I'll flush that one over here. So this is 3, -4, 5. -2, -4, -6. And -44, -8, 20. Okay, this one is actually easier to see, so I'm going to color code it and then we'll swap this over. Okay, so here in pink, I have the original two vectors. Here in black, I have their cross product.
Mm,
You can
Okay.
see we're forming a 90-degree angle with both of those vectors in 3D space.
Yeah.
All right, as long as your cross product is positive, you're going to follow the right-hand rule. So for this one, let's see if I can turn this. Come down. Maybe. All right. So if you put your thumb in the direction that the dotted line is, roughly, just in front of your computer, and you put your fingers pointing in the direction of the fat pink line, your palm should follow the direction that the black line has. Okay, so let's see if I can
Maybe.
turn this in a way that we can do that. Let's keep changing which one's dotted based on which one's on the bottom. uh, Okay, maybe here-ish. So your fingers of your right hand, if you point in the direction the dotted line is showing right now, thumb in the direction that your solid pink line is showing right now, your palm should show the direction of the black line. Does it work for you?
I don't really understand.
Let me turn my camera on really quick.
Maybe.
So,
Maybe. Maybe.
start video. Here we go. Hi.
Oh, hello.
Okay, so I've got my right hand here.
Yes.
So I'm gonna try to orient this like we've got on the picture. So I've got my fingers here are going to point in the direction of this dotted line. I'm gonna
Okay.
tilt my thumb so it's pointing in the direction of the solid purple line. And then my palm pointing upward here is the direction of my solid black line.
Oh. Yes, I think I did it.
Okay, cool. So this becomes really important once we start talking about torque. Torque is three-dimensional forces with a direction. So it'd be like getting leverage. So with a lever arm, if you had, I'm gonna draw really quick and turn my video off. Actually, got a wrench. I'll be right back.
Okay.
All right, so I pulled two. So I've got a normal wrench that I can use for bolts here.
Yeah.
I also have a hex wrench here.
Oh, yes.
Okay. So the purpose of both of these is to give you leverage when you wanted to spin, right? So I'm going to simulate with my Coke top here.
Oh.
Okay. It's massive overkill to open this. I actually don't know if this is going to be wide enough. I think I'm just not wide enough, but something different. Okay, some hand sanitizer.
Yeah, okay.
So just change my size here. Okay. So I've got my hand sanitizer here attached to the wrench, and I've got my cap inside. If I'm going to spin this, then looking from the top, if I start to push in this direction, so clockwise, what do you think is going? What do you think will happen if I push clockwise? So, like this.
Clockwise.
Will the cap go in or out?
The cap will go in.
Okay, cap will go in. So I'm pushing clockwise and nothing's happening because my cap's already on. But okay, so if I push counterclockwise, what's going to happen?
The cap will open.
Cap will open. Okay, the reason why. So when I push counterclockwise, sliding, that's it. Oh, there we go. Okay, I've got the cap off. Cool. It's really screwed on actually. But it is coming off.
Oh.
There we go.
Yay.
Okay. So the reason why that worked, so looking again from the top, I actually have two vectors here. So we've got a displacement vector that is what the wrench is doing. So I've got one
Yep.
vector going this direction, right? But I've also got the vector of my hand pushing on this. So going this way from the top down. So two vectors, one displacement for the wrench, two my force pushing on this. Okay, looking at those with our right hand rule, I've got the vector of this wrench, which I'm going to model with my fingers. The vector of our force, I'm modeling with my thumbs when I move that in the right direction. And you can see the resultant cross product when I multiply those together should be in the direction of my palm facing you right now, which is outwards. So by spinning this, I've created some torque that actually pulls up.
Oh, okay. Oh.
Rescrew this before I forget. The same thing happens when we use a hex wrench. So
Yep.
what we're doing is we're creating a bunch of torque that can drive my bolt in, as long as I'm spinning in this direction. So again, in order to figure out which direction to spin, I could use right hand rule. So in this case, I'm gonna set my fingers equal to one of these directions. So I'll go ahead and set my fingers equal to my source of leverage, thumb equal to where I want to spin this, and I'm going to end up with pushing outside of my palm the resultant force. So here's, okay, I've got a force that I can use where I'm going to spin this here. Okay, so you can see what's happening. I've got my fingers right now are representing the displacement vector to the center point, which I've raised with a wrench, but this part isn't actually doing much. This part's where all the action's happening, because that's giving me my leverage. So I've got my fingers in that direction for the displacement vector, my thumb in the direction that I'm going to spin this. And you can see from my palm the direction that the resultant torque is going to occur from. So by spinning in this direction, following my thumb line, I'm actually going to create a torque that drives the bolt into the table.
Okay.
If I want to drive the bolt out of the table, I can reverse it. So push in the opposite direction around my leverage arm. And now my palm is pointing upward, showing me what will happen to the torque. Okay. Let's see. Do you still see the screen?
Oh, your mic is, I cannot hear you well.
Okay, let me turn this back. Can you hear me now?
Yes, I can.
Okay, cool. Can you still see the screen?
Yes, I can.
Okay, so the cross products inner IJ definition, we'll need to use our create a matrix and then get the cross products of each one to get your IJK definition of your cross products. You end up with a resultant vector. With your dot product, you did not end up with a vector, you ended up with a single number. And that's because your scalar dot product is telling you how much force or how much of your vectors are acting in the same direction. Okay, here's what that looks like. So for your dot product, I had two vectors, vector A and vector B. Vector B has some component that is also acting in the direction of A. All of A's magnitude is going to be added when we get the dot product. So in this case, the magnitude of the second vector running parallel to the first vector is B cosine phi. When we multiply them together, I will get the dot product. So that's vector 1 times vector 2.
Oh, can you explain it again?
Yep. So our scalar dot product formula is AB cosine phi.
Yes.
Which is here again, AB cosine phi. So what that means is this b cosine phi is giving us the component of vector b. It's a lot bigger. The component of vector b that's acting in the same direction as vector a, or this part of our original b vector. So if I take just this part, b cosine phi, and I multiply by the magnitude of vector a, then I'll end up with the dot product.
Yeah. Okay.
So let's give an example of where this is going to show up for dot products. So here I've got a box and we're dragging it along a table.
Yep.
So this table, if I want to figure out how much, or this box, if I want to figure out how much work is done on this box, my formula for work is work is equal to force dot displacement, or F dot X. Problem is, both of those are vectors. My displacement has direction and my force has direction.
Yep.
So in this case, I'm pulling a box with a rope. That box is also moving some distance, so that had some displacement, right? So the work, the amount of energy that we needed in order to move this box from point A to point B would be this force times the displacement, but it wouldn't be the whole force that you're pulling on the rope. It would only be the component of the force you're pulling on the rope that moved in the same direction as the displacement. So here's what that means. If I take this whole force and I take our component of that force that's acting in the same direction of the box's movement, or this horizontal component for us, and then multiply by our displacement, I'll end up with the total amount of work that we needed in order to move the box.
Okay.
That work would be given in joules if you're in the metric system. Your joules is Newton times meters. However, there are still other units that we use for energy, depending on what we're talking about. So nutritionists usually talk about calories. There is calories is a measure of work and energy as well as joules. So it's sort of like miles versus kilometers. It's just two different systems that we're converting from. So calories to joules. 1 calorie is 4 joules. So what we could do is figure out how much work, that's a Newton times meters, we're actually doing to move the box. Once we have that in joules, we just use our conversion factor. So divide by 4 point, whatever that number was, and we'll end up with how many calories we have. Any questions on this one?
Oh,
So
no, I'm okay.
dot products or cross products? Okay. I've talked about wrenches. I think that's it as far as the hard stuff for this next unit goes.
Okay.
All right, so that's an hour right now. I polled all the calculus students, and the only time they're actually available to meet is starting at 8 o'clock on Saturdays. Is it okay? Is it okay if we start the same time that we did today? So it's half an hour later than expected, but that gives a little bit of time if the calculus students need it.
It's okay. I'm okay with it.
Okay, thank you very much. Sorry about the delay.
It's okay.
Okay, so I should have the next assignment up at some point, either tonight or tomorrow. On the same website. And those assignments are going to be the same as the picture posted to the teams though. So if you want to get started beforehand, you can do that already.
Okay.
All right, thank you very much for coming. Let me know if you've got questions along the way.
Okay, bye-bye.
Bye. Mm.